Hi there. So today I'd like to talk to you about the Compton Effect. And the Compton Effect is named after its discoverer, Arthur Holly Compton. Compton was an American physicist. He was born in Ohio in 1892. And he discovered the Compton Effect and shared the Nobel Prize in 1927 for this work. In October of 1941, after he was already famous, he wrote a report on the practicality of the atomic bomb with Enrico Fermi. And in 1942, he became head of the Manhattan Project's metallurgical lab, and his responsibilities included producing nuclear reactors to convert uranium into plutonium. And he helped find ways to separate the plutonium from the uranium to design an atomic bomb. Now, of course, all this work was top secret, so he used a fake name, Mr. Comus here, when he worked at the Hanford site when he worked on the Manhattan Project. So to talk more about the Compton Effect, which bears his name, I want you to first place yourself in the perspective of a physicist in the early 1920s. Now remember, the photoelectric effect paper that Einstein is so famous for and won the Nobel Prize for was only published in 1905. So in the early 1920s, the particle nature of light was still being debated. And so what they wanted was another experiment that wasn't the photoelectric effect, that independently verified the particle nature of light. And the Compton Effect definitely did that for them. It gave clear and independent evidence of particle-like behavior of light, in this case, X-rays. In 1922, Compton observed the scattering of X-rays from electrons in a carbon target, and he found that those scattered X-rays had a longer wavelength than those that were incident upon the target. To describe his experiment a little bit, he used an X-ray tube which generated molybdenum K-alpha X-rays. Of course, an X-ray tube is just a filament that you pass a current through, and then that ejects electrons. And you use a voltage to accelerate those electrons to high speeds and smash them into your target, in this case molybdenum. That creates X-rays, both bremsstrahlung and characteristic X-rays. Of course, the characteristic X-rays will have a much higher intensity, will be much brighter than the continuum behind it from the bremsstrahlung. And so it's those X-rays that Compton used to shoot a carbon target. Now, the X-rays, here depicted as a red beam in this little cartoon, hit the carbon target, and they were scattered at a variety of angles. This picture only shows them scattered at 90 degrees, but he did in the experiment scatter them at a variety of angles and put his detector in different places. So the X-rays came in, they strike the carbon target, and then they were scattered. And to prove that those X-rays had a different, longer wavelength, and remember, longer wavelength means a lower energy photon, he scattered them, diffracted them from a calcite crystal, and used the ideas behind Bragg scattering and measured the angle at which the X-rays were diffracted and used that to determine what their final scattered wavelength was. He then plotted the values for the initial beam, the forward scattered beam, which was elastic collisions or X-rays that just passed right through the target unscattered. So he plotted those X-rays versus the scattered X-rays at different angles. And he showed that the wavelengths were longer for the scattered X-ray photons than for the incident beam. Now, he described this with an equation. He derived it from first principles, this equation, using energy and momentum conservation techniques. Basically, he set it up so that it was just like a momentum and energy conservation equation that you might do in an introductory physics class with billiard balls or something like that. So he treated his incident photon as a particle that had a momentum, h over lambda, and it scattered from a target electron that was initially at rest. That caused the electron to kind of move off. We'll call that the recoil electron, and then the scattered photon would move off at a different angle. The angle of the X-ray would be theta here in this picture, and phi would be the angle of the scattered electron. He came up with this equation that he derived from the scattering equations, the momentum and energy conservation equations, and this is the Compton scattering equation that he's so famous for. And we'll go over it more in a second. Now, according to the classical theory, you shouldn't treat photons as particles. Instead, you should treat them as an electromagnetic wave. If that were the case, if you had an electromagnetic wave incident on an electron, remember it's an oscillating electromagnetic field. And so if your electron is here and the electromagnetic field comes in and it's oscillating with some frequency, then that's going to drive an oscillation in your electron as well, okay? It drives it back and forth. Accelerating charges are going to radiate away that energy. And so what should happen is, classically, that electron should oscillate and that should emit radiation within a range of frequencies. But that's not what was seen in the Compton effect. Compton actually proved that instead of a range of frequencies or wavelengths, the scattered X-rays only had one specific frequency that was described by his Compton shift equation, which was derived from momentum and energy conservation principles, treating the initial and final X-ray photons just like they were little tiny billiard balls. So the results could be explained by treating those photons as point-like particles. Remember that the energy of a photon is HF, right? And then if you set that equal to the energy, which is equal to PC, which comes from our energy momentum relativistic relationship, E squared is equal to P squared, C squared plus M squared, C to the fourth, right? Setting M equal to 0, then you get E is equal to PC. And this means that photons have momentum HF over C, or H over lambda. So your initial incoming X-ray photon has a momentum H over lambda. So also your final scattered photon would have a different momentum, H over lambda final. Now you can also apply conservation of energy equation, saying that your initial photon has an energy HF initial, and then your scattered photon is going to have a shifted lower energy HF final, and then you've got your kinetic energy of your electron that gets scattered, and that's where the rest of the energy goes. So he used those equations to derive it. I'm going to do an example problem at the end of this lecture that I think will illustrate quite well the momentum and energy conservation principles for the Compton effect. So let's go over his Compton shift equation. Basically, the Compton shift equation tells you what the shift in the wavelength is. So you have delta lambda here is equal to lambda final minus lambda initial. Your final wavelength will be longer than your initial one. And then that's going to equal to h over mc, where h is Planck's constant, c is the speed of light, and m is the mass of that scattered electron. And then you multiply that times 1 minus cosine of theta, where theta is the angle at which the X-ray is scattered. And this is the Compton shift equation. Now that factor h over mc, those are all constants. And so you can solve for what that factor is. And this is called the Compton wavelength. The Compton wavelength is 0.00243 nanometers. So let me go through an example problem with no further ado. Find the shift in the wavelength for an 80 picometer X-ray that's scattered 120 degrees by the target. Find the angle between the direction of the recoil electron and that incident photon, and then find the energy of the recoil electron. Now this is a little more complex than just a straight up application of the Compton shift equation. I'm going to have to also, in addition to the Compton shift equation, solve for the angle and the energy of the scattered electron. And to do that, I'm going to have to apply momentum and energy conservation equations. But first, let's go ahead and solve for what the wavelength of the scattered photon is. And we're going to use the Compton equation to do that. So delta lambda is equal to 0.00243 nanometers, that's that Compton wavelength, times 1 minus cosine of theta, and here theta is 120 degrees. That gives me 0.00365 nanometers for the wavelength of my scattered photon, or 3.65 picometers. So lambda final, then, would be 83.65 picometers, because my initial photon had a wavelength of 80 picometers, and then my scatter would be 3.65 picometers longer than that. Now, I'm going to use conservation of momentum and energy to solve. I thought it would be helpful if I drew a little cartoon of what the initial and the final conditions are. Here, my initial condition is on the left. It's my incoming photon, okay? The electron is initially at rest and isn't pictured. My final condition is the photon being scattered off at an angle of 120 degrees, and then my electron moving off at a different angle that we'll have to solve for, here, phi. So remember that when you do conservation of momentum and energy, you've got to have, for conservation of momentum, your initial momentum equal to your final momentum. Momentum's a vector, so you're going to have to break it into its x and y component parts. I've set it up in this example so that my initial momentum of my photon is all along this x-axis. So P initial is equal to E over C times I hat, where I hat is the unit vector in the plus x direction. Now that E over C becomes H over lambda initial, and that's in the I hat direction. So P initial has to equal to P final. Now my scattered photon and my scattered electron have both x and y components, and that's reflected here. The final momentum is h over lambda final, and then I have to take my components, so I've got cosine of 120 in the I hat plus sine of 120 in the j hat. Now my final momentum of my electron I'll call our P sub e, and then the components of that would be cosine of phi in the I hat plus sine of phi in the j hat. Now note that it's easier sometimes to just treat the x and the y components as completely separate from one another in different equations. So that's what I've done here. For the y direction, I've got no initial momentum. All the momentum is in the x. So for initial y momentum, I've got 0. And now I've just taken the j hat stuff here from the top equation and put it in one equation. So 0 is equal to h over lambda final times sine of 120, that's from my photon, plus p sub e sine of phi, that's from my electron. Now I'm going to use that equation and solve for sine of phi. And sine of phi is equal to minus h over lambda final times sine of 120 divided by the momentum of my electron. Okay? Now this is troubling because I've got two unknowns here. But I do have another equation, and that's my equation for my x components, so maybe that'll help. For the x direction, I have h over lambda initial, that's my initial x momentum, equals h over lambda final times cosine of 120, that's the x final for my photon, plus p sub e cosine of phi, which is the x momentum for my electron. Now I can rearrange that equation and solve for cosine of phi, and cosine of phi is equal to h over lambda initial minus h over lambda final cosine 120 divided by p sub e. Alright? So I've got a sine of phi and I got a cosine of phi. What I can do is I can divide those two things and get a tangent of phi. So I've done that here in the next slide. Tangent of phi is the ratio of my sine and cosine expressions from the previous slide. Now the nice thing about taking that ratio is a lot of things cancel. The momentum of the electron appears on both the top and the bottom of those equations, and so I can cancel that out, which gets rid of one of my unknowns, and that's great. I can also cancel out h. It appears in every single term, and that makes my calculations, what I plug into my calculator, a little bit simpler anyway. That's where I always screw up, plugging things in the calculator. So I've got here minus 1 over 83.65 picometers times sine of 120 divided by 1 over 80 picometers minus 1 over 83.65 picometers times the cosine of 120. All right? When I do that, I get that ratio, and it's 0.56. And that gives me a phi of 29 degrees. So I've solved for the angle of my scattered electron, which was one of the things it asked me for in that original problem. Now for the rest of it, to get the energy of my scattered electron, I can just use energy conservation equations. And I get that the initial energy of my system is the initial energy of my photon, hc over lambda initial. And then my final energy is the energy of my final scattered photon plus the kinetic energy that gets transferred to that electron. So hc over lambda initial is equal to hc over lambda final plus that kinetic energy of the scattered electron. Now, it might be handy to know that h is 4.136 times 10 to the minus 15th eV seconds. And c, of course, is 3 times 10 to the 8th meters per second. If I multiply those two things together, sometimes that's a handy sort of combined constant to know because it appears in a lot of equations. So that's 1.241 times 10 to the minus 6 eV meters, or 1241 eV nanometers. So now I'm going to plug in 1241 eV nanometers into my HC for that equation. So then I have 1241 eV nanometers divided by 0.08 nanometers, that's my initial energy, equals to 1241 eV nanometers divided by 0.08365 nanometers, plus that kinetic energy of that scattered electron. So now I can just subtract those two fractions and get the energy of my scattered electron, and that's 676.9 eV. So I've done it. I've solved. Now what did this tell us? First, the Compton effect illustrates that you can treat an X-ray photon just like you would a billiard ball in a collision problem from an introductory physics class. So what that tells us is light does act like a particle in this case. It has an initial momentum. It collides inelastically with an electron, and it transfers some of its momentum and energy to that scattered electron, just like a billiard ball would. That scattered photon then has a lower energy, and the remainder of that initial energy goes into the kinetic energy of the electron. So that was an independent verification of the particle nature of light that didn't depend on the photoelectric effect. And that was why the Compton effect deserved the Nobel Prize, which he received in 1927. All right, thank you so much, and I'll see you in class.